Let me get this sucker rolling. Get up to the smart board and we will see what's what. All right. All right. So what I wanted to do today was talk about adding and subtracting fractions, okay? And I know that we all have done adding and subtracting of fractions, and one of the rules of adding and subtracting any fraction was that you always had to have what was called a common denominator. Well, that doesn't change at all with when we're talking about rational expressions. So if we have common denominators, basically what happens is we wind up combining our numerators just like you would with any other normal numerical fraction. For example, if we have something that looks like this, where I have 4 over 3x plus 5 over 3x, when I look at that is what we call a rational expression because it's polynomial divided by polynomial. Even though that numerator's polynomial is a constant, it's still technically called a polynomial. Yeah, it probably wouldn't be a bad idea to just keep, however you want to take notes is how you take notes, but I strongly recommend writing things down as we go through them. So just like you would have before, if you happen to have, 4/3 plus 5/3, what you would wind up doing is that you knew that you had a common denominator, and you'd have your 4 plus 5, and you'd wind up with 9/3, and then you would simplify that, and you'd wind up with 3. Well, this is the exact same process. It just so happens that there's a variable thrown in, okay? So this still has a common denominator of 3x. So we add together the numerator just like you would before, and we'd wind up with 9 over 3x. And then lastly, we would have to simplify that out just like we did yesterday, and you'd wind up with 3 over x. So the process by which we're setting up, and I want to call it simplifying our fractions, is the exact same way as you would have it any other time in your lives when you had fractions. You're still getting a common denominator and working through it, okay? It works the same with subtraction. Excuse me. It works exactly the same when we're dealing with subtraction. When we look at this happens to have binomials for denominators. So in this case here, we know that x plus 3 is the same thing as x plus 3. So I would just put that as one giant fraction, and our numerator would be 2x minus 4. Now, in this numerator, there's nothing left for me to combine, but I do take a quick look, and I notice that 2x minus 4 can be simplified a little bit. We can get a GCF of x minus 2, and usually when I do this, I just take a quick look and see, is there anything that can simplify out, the x minus 2 over the x plus 3? Since there really isn't, then I just don't worry about it, and then I'm done, okay? We can't simplify this any further. Just like you were doing a little bit of this yesterday, but obviously with a lot of all that stuff going on, all right? So vaguely, it's fractions with a step, if we want to call it that way, all right? So now, what happens when you had to do stuff like this? When you had, fractions, and I like to go back and forth between numerical and the variable stuff, because to show the correlation between the two is relatively simple. Here I have 2/3 plus 1/2. What we would do then is we would figure out, do you guys remember the term least common denominator? What that meant was we were looking to see what's the next smallest number that both a 3 and a 2 goes into. And I picked numbers that were prime to start with, and I'm going to show you an example here with non-prime numbers in a second to show how we can simplify this out and how that's going to parlay into working with our polynomials as well. So do you guys all agree that a common denominator here would be 6? The next number that both 3 and 2 goes into is a 6. Okay. So what we have to think of now is, excuse me, can I also write that as 2, well, I'll do it in order. 3 times 2 just for right now, is that okay to write that as 6? So if I'm looking at the fraction on the left, it has a 3 already in the denominator. It needs to be multiplied by 2. Now, what I do here is I multiply both the top and the bottom by 2, or in essence, in this case, 2 over 2, because 2 divided by 2 is how much? 1. So remember, when you're multiplying something by number 1, you don't change that something. What will happen here is we're just changing the way it looks. So we wind up with 2 times 2 is 4. And then over here, we have to multiply top and bottom by 3. And I get 3. So this becomes 7 over 6. This was kind of the long way that you guys learned how to do all of that years and years ago. Now, one of the other ways that I like to show is when we have, oops, let me just slide this over just a little bit. I'll leave this, maybe. Put this on the same screen here so you can kind of see this. Same idea. If I say that I have 3/8 plus, oops, sorry, that plus sign looks like junk. We'll say 5/12. Do you guys remember how you would write things in terms of prime numbers? Does that vaguely ring a bell, rewriting composites in terms of primes? Do you guys remember what the difference between a composite and a prime is? Remember, a composite number are any numbers that are divisible by more than just 1 and itself. Prime numbers are only divisible by 1 and itself. For example, 8 I can divide by 4, I can divide by 2, I can divide by 1, I can divide by 8. It's a composite number. Same thing with 12. Whereas the number 3 or the number 2, those guys are only divisible by, well, 3 is only divisible by 3 and 1, 2 and 1. So those guys would be considered prime. So what I'm going to do is I'm going to rewrite 8 as a product of prime numbers. Hopefully you guys remember this, that 8 is 2 times 2 times 2. You okay with that? 3 is still in my numerator. Okay. 12, on the other hand, is what? 4 and 3. So I'm going to say 2, 2, and 3. And now I have my denominators written out in terms of primes. Okay. So in order for us to get what we call our least common denominator, what we do is we look at our denominators now to figure out what do they have in common and then what's left over. So here, well, they have one set of 2's, another set of 2's, and what's left over? A 2 and a 3. That's how you guys used to get the least common denominator, by pulling out the sets that were in common, writing those down, and then just filling in whatever was left. Does that vaguely ring a bell? Does that vaguely look familiar from way back when? Sort of, yeah. To be honest with you, I think this is easier to see once we start talking about it when we look at the actual terms, when we do our factors. I think it winds up being even cleaner to see this as opposed to just prime numbers, okay? So from here, our total, or the next number that both 8 and 12 will go into would be 2 times 2 times 2 times 3. In other words, 24, which makes sense because if I do factors of 8, it's 8, 16, 24. 12 is 12, 24. It's just writing it in terms of primes. So let me rewrite this down here a little bit. So we have our 2, 2, 2, and a 3. This value of 3 has 2 2's. Sorry. This value of 3 has the 3 2's in the denominator. It needs the 3. This 5 has 2 2's and a 3. It needs another 2. So our numerator becomes 9 plus 10 over 24. That was kind of the longish way that we went through simplifying fractions. What part, Senya?
Wait, how did you do the top part?
The 3 times 3? Okay.
Yeah.
So what happens here is that we have this 3 over, I'm sorry, it was 2 times 2 times 2, and it was 5 over 2, 2, and a 3. We knew that the common, you were okay with the denominator, right?
Yeah.
Okay. So what I'm doing here is, if you look at this denominator, it has it has 3 2's. Do you agree?
Yeah.
What's it missing?
The 3.
Exactly. That's exactly right. So we take that missing 3 and we multiply it to the numerator. And I do the same thing with the 5. The 5 has 1 2 2's, so it has 1 2 2's, and now it's missing and a 3, and it's just missing another 2.
Oh, okay. Thank you.
Okay. There's multiple ways of doing this. I'm trying to show you the least messy. Okay. All right. So then you just wind up putting it all together, and what I said, it was 19 over 24. Okay. So let's look at this in terms with variables, with our polynomial stuff. All right, and see how you should notice how it kind of matches the same procedure. For example, start with something super simple. I have 2x over x plus 5 plus 7 over x plus 5. Do these guys need a common denominator? Yep, they don't. So I can just say, all right, x plus 5, and then my numerator is just combining like terms, 2x plus 7, and I'm done. What's going to change is when we have non-common denominators. For example, if I say we have, x over x minus 3, excuse me, plus 3 over x plus 2. Those two denominators are different. And one of the easiest things that we learned way back when to get a common denominator was sometimes to just multiply the two denominators together. Well, that process really doesn't change. What is it? X minus 3, x plus 2. This fraction on the left has an x minus 3. It needs the x plus 2. This fraction on the right has the 3. It needs the x minus 3. All that's left then is to multiply out your numerator and combine like terms. I never want you guys to ever multiply out your denominators, okay? Don't worry about that. I'm only going to ask you to always multiply out and combine like terms of the numerator. So if I do that, I wind up with x squared plus 2x plus 3x minus 9. So my final answer would be x squared plus 5x minus 9 over x minus 3, x plus 2. And to be honest with you, I'd say 80%, 85% of the time, maybe even 90% of the time, there's nothing left for you to do in the numerator. Very, very rarely would there be something left for you to do, okay? Do you see how that works really fast when you have the actual terms for the polynomials together? You put them together, what do they need? This one needs the x plus 2, the one on the right needs the x minus 3, okay? May? All right, cool. All right, let's see. Make it even, let's go back, we'll go back a step, make it a little bit easier. So I have 7 over 5x plus 8 over 3x. So in looking at this, do these denominators have anything in common? All they have in common is the x. Well, what's left? A 5 times a 3. So my least common denominator will be 5 times 3 times x, otherwise known as 15x, but I'm not going to write that quite yet. Because by leaving it in their separate pieces, I can see what each individual fraction needs to be multiplied out. So fraction on the left has a 5 and an x. It just needs the 3. Fraction on the right has the 3 and the x. It needs the 5. Let's see, 21 and 40. And I'm done. Should we try something with a little bit of factoring now?
No, we're good. We're good.
The fish method, is that the one we were talking about when you come across what's over here and what's down and back or something like that? I never learned what it was technically called, the fish part, but this is the way that I've always done it. It's a little bit different than textbooks. I don't know if you guys noticed I'm a little bit off, but I try to make it as simplistic as I can. Okay. If there's another method that works for you that you're okay with, that you've done in the past and you're solid with it, that's fine. All right. I'm not to say the methods that I'm showing you every single day are always going to be perfect, but I'm going to show you methods that I think that have been the easiest for the majority of most students to work with. Oh, I got you. Okay. So just like yesterday, when we wound up with polynomials that had higher degrees or things that you could wind up factoring, what I want you guys to think of is this, just the same way you were doing the problems yesterday. As soon as you started writing them down, you were factoring them as you were going. This is another good example of something that I would do that to as well. So what I would be doing, excuse me, what I would be doing is I'd be writing it down like this. X plus 1 over, what times what's 4? It's 4, that's 2 and 2. So it'd be over x plus 2, x plus 2. Now this is a subtraction one. And then numerator of 2, this is a difference of squares. And now again, I have to figure out my common denominator. So do either of these denominators have something in common? Well, they both have an x plus 2. So I'm going to write that down. And what's left? Well, I have another x plus 2. And then I have an x minus 2. Okay. Think of this as, you know, a denominator of 4 and a denominator of 6. 2 times 2, 2 times 3. What did they have in common? One set of 2's. What was left? A 2 and a 3. It's kind of the same basic idea, but yet we're dealing with it in, I should say this, terms of our factors, okay? So we restart. Fraction on the left has an x plus 1. It needs an x minus 2. So x plus 1, x minus 2. Here's the one part that most people mess up. Whenever it's a subtraction problem, do yourself a favor and make a bracket to remind yourself that you need to remember to distribute the negative all the way across. Fraction on the right has the x plus 2 and an x minus 2. It's missing one of the x plus 2's. Okay. Now, I know that I got a whole lot of stuff I have to redo in my numerator. So what I do next usually is just work with the numerator. And then when I'm done, I'm going to rewrite my denominator at the end. That way I don't have to keep rewriting it because it's just going to waste space in all honesty. So I'm going to slide this up just a little bit. So my numerator, if I FOIL this out, I'm going to get x squared minus 2x plus 1x with minus x minus 2 minus the quantity 2x plus 4. So this becomes x squared minus x minus 2 minus 2x minus 4. So this whole numerator works out to be that after you multiply everything out and combine like terms. All that's left to do then is put that over and you're done. Never multiply out your denominators. It's a waste of time, okay? Could you rewrite that denominator as the quantity x plus 2 squared? Sure, absolutely, if you wanted to do that. That's not a big deal. I'm never going to say no to writing that out. I usually won't, just because it takes a little bit of time and it's not the end of the world. If you do wind up writing it out like that, that's fine. I'll mark it right. I'm not going to mark it wrong on you. You're doing it right, okay? Just remember, when you're working with stuff like this, The tricky ones are always subtraction, because it's not that the math part of it is hard, is that you guys just tend to make a stupid mistake every once in a while and you forget to distribute out the negative. That's why I always say, whenever you have subtraction, put a hard bracket in, because it's obtrusive looking and it will remind you to go back as you're working through it to fix it later on, okay? So what I did with formative stuff is that I basically took the 7 or 8 questions that I was going to give you guys tomorrow. I just opened it up a day early today, which means with the stuff that I've shown you here, you should be able to get at least 3, if not maybe 4 of them through, because tomorrow we're going to talk about a little bit more of this with a little bit higher degree denominators where you have to do a couple extra steps here or there, and what's left over with what's called a complex fraction, which is just basically fractions divided by fractions within adding and subtracting and all that all at once. They look like crap, but they're pretty simple to work with. It's basically like doing 2 of these problems at the same time, okay? So give those a shot. The stuff that I put up there today, I know that I see you guys again tomorrow. This whole assignment's not due till next Monday. I just wanted to put it out there a day early. I figured it didn't hurt anything to try to get out ahead a little bit of this. That way we can take a little bit more time tomorrow to do a couple extra ones, as well as spend some more time on the complex ones, because those can get kind of funky if we're not careful, okay? And then that still gives us next Monday to do equations, which are really quick. And then next Wednesday to go over any last minute questions. And then for you guys, then it'll be the following Thursday before our Thanksgiving break and parent teacher conferences stuff to have our quick little, I think I'm going to have this be maybe 5 questions, 4 or 5 questions total. It shouldn't be so terrible to work itself through with some of this stuff to go into break then and go from there. All right. Questions at all, guys? Cool. All right, if you guys want to bail out, that's cool, and I'll stick around with you, all right? Let me switch computers.